back with the community. Last year I was here, didn't say much. I was transitioning over to Intel. Since then, we've been very active in figuring out a strategy for Intel around Exascale, and I'd like to talk to you a little bit about our thinking. But the bottom line is that we see a big intersection between big data, but not the cloud, but what we call fast data, which is HPC storage. So that's kind of the message of my talk there. We're targeting an Exascale machine in the 2018 to 2020 timeframe, and you know, to contrast this activity from the way Intel has approached supplying component parts to the ecosystem in the past. We're taking a systems view to this, and the Lustre parallel file system is an integral part of that strategy because it's a open source, community developed thing, and it also enables us to have the IA architecture in the storage platforms as well as the new platforms. So in heading to Exascale, our design focus is enabling end user applications, and there's only three basic problems to get there: scalability, scalability, and scalability. So there's the hardware scalability. Our approach there is to have a simple node as possible, have as many of the functions that are typically on the motherboard and in other parts of the chassis or rack on the processor, integrated interconnect, and keep it very simple. The MTBF needs to improve by about an order of magnitude over what we project will be the standard Intel roadmap. In addition to that, we have to improve power consumption by over a factor of 2 in order to get it within the envelope here. Another thing that is a distinct change for Intel as well is scalable software. We currently are mostly in an enabling role in terms of software on platforms, but with the Exascale system, there's a very strong interaction between the system software and the applications and the hardware. So we're taking a hierarchical systems approach to the system software. Basically, it's an idea where we take a very hard problem, which is have a full operating system on 100,000 nodes, and we solve it into 2 problems. One that is merely difficult, and the other one is a solved problem. And the merely difficult problem is function shipping off of the compute nodes to the operating system nodes, and then having a standard Linux distribution on the operating system node with a Lustre parallel file system client there. And then the scalable applications is a critical part. It's anticipated that the Exascale machine will have over 1 billion way of parallelism. So what we're thinking about there is asynchronous communications and I/O, as well as enabling applications to do data transfers in a method that is fundamentally there. This is our projected software architecture for the Exascale platform, and again, Lustre is a key component of that. And the message here is that we're not forgetting storage. Storage is a major part of the overall system Exascale strategy. One of the things that I noticed while working at Livermore was that the usage model for applications is changing rapidly as we went through the terascale era into the petascale era. And one of the fundamental shifts is that they're not just running one application anymore. They're actually running what we call a quantification of uncertainty framework, which drives a bunch of application instances on the machine. Of course, there's the very large application run that takes the whole machine and runs for months on end. But then there are a series of runs that are much smaller that explore the parameter space of the application area in order to quantify the uncertainty. So it's no longer good enough to get the predictive simulation answer, but you have to also be able to have some indication of what the sources of errors are in that simulation, how big those errors could potentially be, how they impact the solution, in order to inform the scientists about what their confidence in the solution. So if you're going to make predictive simulation guesses and then make decisions based on those simulations, you want to have an understanding of the confidence that you can have in those simulations. So now what people are developing is a UQ framework, which is basically an application-specific or domain-specific driver for a bunch of applications. And those applications typically use a positive parallel file system, but in order to keep track of massive amounts of data that they have coming out of their application, they put in a parallel database within their application. And that allows them to have objects that are in the application and then turn that into block I/O. And then they go to the block I/O through the POSIX layer and then down to the block servers. And all of the block servers today are being implemented as object servers on the back end and object transactions with the devices. So we have object at the top, objects in the middle, and object at the bottom, and they're not connected. So the aha here is, hey, let's take the objects that are in the application and drive them all the way through the stack down to the device. Now, there's a fundamental change that has to happen here. Two fundamental changes that have to happen here. One, we need a different interface besides POSIX. Okay, everybody willing to give up POSIX? Raise your hands. Okay, well, it turns out the application guys, when I go over and talk to them, and I say, this POSIX interface that was designed in the 70s, it's been pretty good so far, but we're running out of gas with it. How about we do objects instead? They go, we've been asking you guys for object interfaces for the last 5 years. Where have you been? I mean, it's not like there's a resistance to this. It's like, come on, guys, get on with it. The other fundamental shift that has to happen is that down there on the block device, we need to be able to have user-defined objects transacted with the device on there. And so that means that the device needs to be adaptive to the application as opposed to have a fixed object or block size down on the device that ripples through the stack and requires the user to perform their data types and so forth back to their internal data structures. The other thing, when I first started thinking about it, I go, oh my God, how are they going to see their data? Typically what happens is people log in and type ls and look at the directory and then go cat files and all that stuff. Man, that's so 70s. That's not what people do today. Scientists today have their data analysis stuff typically written in Python. So the first thing they do when they log in is they hit Python, Python, get inside the interpreter and then read all their data into Python in a single system image, right? Which they're limited in size of the data that they get told in because they're in memory. And then they run scripts on their objects that are now in memory in order to do the data analytics that they require. Why don't we just provide them with a database mechanism that allows them to search and to compute on their objects, not in memory, but in a distributed infrastructure. So it maps very well into what users are already doing. So it's like, the storage community here is actually catching up to where the applications guys are. The other thing is that there's a need for checkpoint restart in these applications. So the green instance here is a series of computations that take place over time, and then the red here is the I/O, defensive I/O for checkpointing. So typically what happens is that all of the computation in a parallel application takes place a couple of time steps, maybe 4 to 8 hours of computation, and then the application takes a checkpoint dump, and then they go back to computing. But what happens is there's an implied synchronization point at the end of that computation, and then again at the end of the I/O, and that happens over and over and over again. And when you're computing, you're not doing I/O, and when you're doing I/O, you're not computing. And so right here, we're wasting the computer, and over here, we're wasting the I/O subsystem, right? And so there's a zero bandwidth required, and then there's maximum bandwidth required, and then it goes back down to zero again. So that's probably the worst possible way to use a parallel file system. Instead, if we had an object model where users could transact their objects with the storage mechanism, notice I didn't say file system, they could start transacting the persistent objects way far in advance in their computation and overlap the computation with the I/O, such that when all of the transactions for an epoch were complete, right, then a new epoch starts. And look what happens. All of that computation and I/O gets compressed down into only computation. So overall, the application runs much farther. And the red part here is the comment that the amount of data being transferred is the same. But what happens is because you're doing it over a much longer period of time, the peak I/O rate goes way down, and you're using the I/O subsystem most of the time, which is a much better way to utilize the storage mechanisms. So overlapping computation and I/O, and the synchronization is reduced. So that wiggly line there is a way to indicate that as soon as this epoch is complete, the computation can proceed. Now, so every individual task doesn't have to synchronize with all the other ones. There's a very loose synchronization that can take place here. It doesn't give you minutes or hours of slot, but it gives you tens of seconds of slot, and that's exactly what we need in today's and in the future computing models. Now, those are the challenges of high-performance computing for Exascale. What I'd like to shift for a couple of slides here is the big data challenge. The amount of data coming out of the internet today is absolutely astounding. These numbers here are unbelievable. It's only the beginning. In fact, IDC storage capacity growth is shown here. The public cloud content thing has a compound annual growth rate, or CAGR, of almost 50%. That means it's doubling in less than 2 years. The public cloud content is almost 60%. The traditional replicated data is a 30% CAGR. Traditional unstructured data, which is archives, is about 60% CAGR. And the typical structured data, enterprise databases and so forth, is about a 30% CAGR. These are phenomenal growth rates. If you think about where high-performance computing growth rate is for processors and stuff, it's in the 10 to 15%, which is a great growth rate, but these far exceed it. So this market is exploding. And these are the sources of the data, and some indications of the sizes here. And again, 7 exabytes of traffic data used by mobile users worldwide in 2011. I mean, one of the criticisms Intel has had up recently, where's your phone? The computer market is moving toward phones. It's not really. With all that data being transferred back and forth, there's really a large server back end driving all those phones, and that's where the big money is in that. So the grand challenge here is with this massive amount of data that's coming through. How do you get knowledge out of that? In this community, there's a perfect example of this with the Target stores, where they were tracking people with their preferred shopper cards and their buying behavior, and they figured out that there are 3 times when people make changes with buying habits. One was when they got married, another one was when they had kids, and the third one is when a family member dies. So they identified mechanisms by watching buying behavior. They could figure out when a couple got pregnant, and they could even predict when the baby was going to be born. And so they did targeting advertising for baby stuff, and got people to change their buying habits to buy more at Target, and doubled in-store volume. Doubled. It's amazing. So there's a lot of money to be made commercially by getting information and knowledge out of these big data. But the problem is with the exponential growth here in data, the budget for IT spending to deal with that is a much lower CAGR, which means that there's innovation opportunity there. So by taking data and thinking about it in terms of getting information out of that, and then prioritizing that information and helping decision makers make decisions. That is the ultimate goal here. And you know, if you think about high-performance computing in the UQ scenarios I was talking about before, what we're trying to do there is create a lot of data and provide information, predictive simulation capability, so that scientists can make decisions. It's exactly the same paradigm. So there's a lot of overlap between what we're trying to do in HPC and what the big data folks are trying to do with all that data out there. So there's been one model out there that has captured a lot of mind share. That's Hadoop. It's a map-reduced data parallel model, and as long as the mapping and reducing steps are well balanced, the tree is well balanced, and you do the computation where the data is, it runs very well. If you have an unstructured mesh, though, trying to figure out the circle of influence of a particular Facebook user, for example, and what the interactions between those circles of influences are, and so forth, that's a very unstructured computation. It doesn't map well onto the MapReduce framework at all. And so what we're looking at Intel Labs and with Carnegie Mellon University is methodologies for doing in-memory graph traversals to identify these connections and figure out new connections from that aren't obvious from the data. The problem is it's unstructured, right? And so what we really need is an I/O mechanism where these guys don't have to bring all of that unstructured mesh, unstructured data into a single computer memory. And so what we're talking about here is the moral equivalent of out-of-core solving of large matrices, right? And so what we want to be able to do is an out-of-core solution using the file system as a caching mechanism to have a very large unstructured database. So to do that, we're working with ManCloud to peel back the Lustre POSIX interface and get at the object infrastructure underneath it and define this new thing called the Distributed Application Object Service, which is objects defined by the end-user applications that works at the scale all the way to exascale and separates the scalable object namespace and allows the application to define metadata for the objects which are searchable, and then have application data in the object, which is the scientific data that's not searchable, and gives us a high level of I/O. So if you think about it, if we have some kind of persistent storage, either on the compute node, or if you remember back to my Exascale diagram, system architecture diagram, on the OS nodes, there's a very fast transaction mechanism between the object, the user application, and persistent storage on the computing device, and then that later dribbles out to a centralized storage mechanism. This is the infrastructure that could allow us to have that very fast transaction mechanism. Oh, and by the way, since it's based on the base Lustre infrastructure with a new Deos Pod API on top of it, we can co-locate the data on the same devices. So you can have a Lustre parallel file system, you can have a simulation data with an object database on top of that. And oh, by the way, we can map the Hadoop file system and MapReduce infrastructure on top of that. And we can also use that for unstructured calculations as well. So if you go and talk to enterprise storage guys, there was a big revolution in storage in the 2000, early 2000 era, which was basically consolidating multiple devices into a virtualized SAN environment that basically shared devices. Now what we're seeing is a commoditization of that market, both on the mainframe side, but on the storage side as well. I/O servers now are predominantly software-based and based on the IA architecture. And what we're seeing is the application servers that are also IA-based and virtualized and those kind of things. So now we have a unified network, a distributed application storage and metadata services. And what we see in the future is that we can virtualize that environment. And there's a big wave of virtualization that's already happened on the application application server to utilize the idle cycles in the enterprise. And HPC, we don't have that problem. Every machine is saturated as soon as it hits the ground. But on the I/O side, we can also virtualize the storage servers. If we virtualize the storage servers, we can, in this distributed application object storage mechanism, we can also distribute methods to operate on those objects at the storage server. And if we do it in a virtualized encapsulation environment, we can impose the right locality, we can impose the right security model and protection safety model for the RAID controller software underneath it. So I'm very excited about extending the computing paradigm from one where in high performance computing we always suck all the data back to the supercomputer to do the data analytics and visualization and stuff, to one where now we can, if it makes sense, if it's data intensive, we can move the method to where the storage is, like Hadoop, except it's unstructured and has an arbitrarily connected graph type structure versus always being forced to move all of that data back to the supercomputer. So in summary, I think that Exascale requires a different HPC storage paradigm, and the users are demanding that be an object-oriented paradigm, object-oriented paradigm where they get to find the objects, not the file system or the devices. Big data and fast data have very similar requirements, and their objectives are very similar, and that market is growing extremely rapidly, and so that's got a lot of vendors very interested in developing technology in that area. And if we can overlap that with the requirements of big data and fast data, I think we can go forward to Exascale and have HPC be the leadership position in defining the technology that is used by both camps. And now we have a much broader marketplace upon which we can base our economic underpinnings of the drivers, the technology drivers for HPC. So let's go fully object-oriented, and the time to do that is now. So that's my talk, big data intersecting with fast data. Thank you.